Morning. Okay, so last time I sort of introduced Gaussian processes, and this time I'm going to sort of in an hour and a half. I was thinking I can speak about Gaussian processes for about 20 hours, so and I have done in the past. So deciding what to say is sometimes an interesting challenge. So in an hour and a half, I'm going to try and give you an overview of deep Gaussian processes and the approximations that enable them. The world is not as Gaussian as we might like it to be. But in fact, it used to be. It used to be very Gaussian indeed. So this is an image of the cosmic microwave background, which is I guess, the afterglow of the universe as it went from plasma, as the plasma disappeared and visible light was available for the first time. And it's actually a Gaussian process. So this is, I think, I'm not an expert in cosmology at all. Is Bruce here? Any other cosmologists here? So I can make up stuff. Good. My understanding, from speaking to those who know, is the covariance function for this Gaussian process is determined by the 6 parameters that make up our universe, including things like the amount of real matter there is in the universe and the amount of dark matter. And what you're seeing here is different densities of that matter and what we have of the observable universe now. So if you simulate cosmology, what you do is this. The modern Earth is a nonlinear function of that Gaussian process. So that's one hell of a GAN. Of course, it's quite a complex function. But that's why the modern universe, is non-Gaussian, because I guess what's going on here, I don't know anything about it really, but my understanding of what must be going on here is the physics at these high energies are such that collisions are occurring between particles, and some of those forces that affect those collisions aren't effective. But then as you start to condense, sort of non-linear things happen. But that would have been an amazing universe. You could have predicted jointly across any part of the universe extremely accurately, in a very well calibrated way, what was going on in the other part of the universe. Only, of course, you couldn't have existed to do it, which is a slight problem. So that isn't the inspiration for deep Gaussian processes, but it would be cool if it was. But you could imagine, so what deep Gaussian processes we're going to do is we're going to start with Gaussian process priors in latent spaces, and then we're going to put a Gaussian process prior over this function. Okay? So you start with a Gaussian process prior, and then you say, this is just another function. So I'm going to have a GP over that. Of course, this function itself that produced this is probably not a Gaussian process. But you can make this function itself more and more complex by composing multiple Gaussian processes together. And that's the basic idea, what I'm going to talk about. Okay, this is Kai Arul Kamaran put this together. So, all right, team, if we want to be taken seriously by the research community, we need to come up with some theoretically driven research projects. One model to rule them all. Okay. Welcome to my life. So somehow, of course, the reason this guy was so angry is because sparse Gaussian processes is not a good name for the approximation. They're not sparse. He should have said low-rank Gaussian processes, which is what I like to call them. But yeah, so it's not the most fashionable area at the moment, but that's fine. Neural networks weren't the most fashionable area 13 years ago, 10 years ago even. So I'm going to start by introducing low-rank Gaussian processes, because these processes are important in enabling the deep Gaussian process models that follow. I'm not really going to show you the details of how that happens, but I just want to give you an instinct for this. And they're also important in scaling up Gaussian processes. So the GP has the following demands. Complexity of computational complexity, I should have said here, is order n cubed, and storage is order n squared. Now, in a low-rank GP, which is often called sparse GP or variational Gaussian processes, the complexity is order nm squared, where m is a user choice. It turns out to be the rank of the approximation you use, and the storage is order nm. Often people worry about the cube, but my experience is storage tends to hit you before cubic. That's because you have sort of infinite time, but you don't have infinite capacity in your computer. So you tend to run out of memory before you run out of time. Where m is a user-chosen parameter. And there's a long history to these. I've put several references. Oh, and before I forget, I forgot to mention it last time. So you can find, let's see if I'm connected to the internet. If you search for Neil Lawrence talks, then you get no internet. Let's see. Here's one I prepared earlier, like Blue Peter. So if you go to Neil Lawrence talks, you'll see all my talks are listed. And if you click on the talks, you'll see you not only have the slides for this, but you have full notes. So if you click on that, in fact, for some reason, the Jupyter Notebook isn't appearing. I need to fix that. Eventually, a Jupyter Notebook will appear here. But as you go down, you'll see everything I'm saying is sort of written there live on the web. Of course, none of you can access that now because the web's not live. And what I've tried to do is give fuller explanations here for things I'll discuss briefly. So this is a much longer document in some sense in terms of the details than I'll present. So what we're on at the moment is this bit here, where I've tried to give references, citations, everything else. I'll turn it into a PDF, put it on archive or something at some point in the long-term future. Okay. So just for if you want the details of what we're doing. And same for last lecture as well. So there's a number of citations and a long history of trying to build these approximations. And what I'm going to show you is one sort of the consensus. There's a really nice recent review paper by Tang Bui and Rich Turner and others summarizing these things. So what's the idea of the approximations we're going to use? Well, I tend to call them variational compression. So we're going to use what I call a variational compression approximation. And what we do is we introduce something we call inducing variables. Now, in other areas, these could be called landmark variables. That's what they're called in the Nystrom approximation. And in Markov chain Monte Carlo, they would be called auxiliary variables. What they are, in this case, they turn out to be like pseudodata. So they turn out to be sort of observations that we don't really make. So instead of building the Gaussian process prior on the observed data that we have in the real world, which we have to store all n of, what we try to do is say, imagine if instead of observing all those n data points, I'd really observe these m data points, where m is smaller than n. And cleverly, you don't even have to have those m data points in the same domain as f. So you can actually say things like, and people don't do this yet, but people should do this. And I think one reason people don't do this is because we haven't had enough deployment of these ideas in practical applications because the software's not been good enough. So they could be the gradient of the function. They don't have to be the function value itself. You could say, I observe the function, I observe its gradient in this other point. They could be convolutions of the function, integrals of the function with other things. People have observed the frequency of the function in the Fourier domain. There can be any linear operator, because any linear operator on f is jointly Gaussian distributed with f itself. So that's kind of the idea. So what we try and do is we compress the information in the training data into these inducing variables, okay? Such that we only have to store the inducing variables rather than storing the whole training data. That's kind of the problem with non-parametrics. Non-parametrics is difficult because you are taking into account, remember I sort of talked about bottleneck, I'll talk about it again. If I have a fixed number of parameters, I have to communicate all the information from my training data to my test data through that fixed number of parameters. One other definition of non-parametrics is the number of parameters grows as your training data grows. So that's what's going on in a non-parametric model. But here what we're going to try and do is squeeze that down into a reduced number of observations that aren't the original data. So we've seen how we went from parametric to non-parametric. Last time I sort of waved my hands a little bit around it. And Gaussian processes are generally non-parametric. This is what I was just saying. So this is the sort of what goes on. This is how I sort of motivated the lecture at the beginning, that the prediction over a test point is given by the observation, or a test vector, the observation at that test for those test vectors given that and given the training data, the classical parametric approach, so I've got an extra bracket there, the classical parametric approach is to look at the expectation of the likelihood under the posterior distribution of the parameters given the training data. And this is what I mean by the bottleneck, that the communication between these guys here and this fellow here is through W. So that's a sort of fixed bandwidth channel. So in a general Gaussian process, though, that's not what goes on. So what I showed you is you can turn a parametric model into a GP and you get a covariance function of this form. And that's a parametric model. In those cases, you can summarize in a fixed number of parameters. But what goes on, what we were going on in a general Gaussian process, is this inner product here. We take the limit, we take the sum of that goes to infinity while scaling down these bases. So there's no longer a fixed number of W. But W, what's basically happening is implicitly W is infinity in here. Yeah? Okay. So the rank of this is at most M. So I should have used K here because I'm using M for inducing variables. And although they're related, they're different. So the rank is at most K. And that's what allows them to be efficient. So in the linear kernel, the rank of this matrix is equal to the number of input dimensions, which is what gives you that computational complexity for a linear model. So for non-parametrics, prediction at new points F star is made by conditioning on F in the joint distribution. So what do I mean by that? Well, I was referring to Y before, but I'm now going to look directly at the function. So I said probability of Y star given Y. But what I'm just saying here is that's true for F star given F, where F is the underlying function, if you remember, before it's corrupted. So Y is equal to F plus some noise. So, yeah, I think I've just actually spoken about that. So what we're going to do is we're going to augment the variable space. And this is the inducing variables. I'm denoting them by U. Now, U is the output value of the inducing variable. Here, it could be living in the same space as the function, but it doesn't have to be. You can have U living as a different type of function, as I said. U could be the gradient of F. And you can build you can build a Gaussian process where you're jointly modeling the function and its gradient. And the way you do that is that KFU is the gradient of K with respect to one of the inputs, and KUU is the gradient of K with respect to both of the inputs. That gives you the covariance function for the gradient. But here, just in general, there's just some set of variables U. Now, very commonly, people do choose U to just be in the same space as F. That's the sort of simplest thing to do. But one of the mindsets I had to get out of is when I'm looking at a Gaussian process over multiple functions, it still exists in this form. So for me, like a multi-output GP still has that. It's still just a Gaussian process. It's just all that happens is you index the different parts of this by the function you're interested in. So this is just a joint Gaussian, and all you're saying is that F and U are jointly Gaussian distributed. So the only constraint on U is it needs to be jointly Gaussian distributed with F. Now, what you do is you look at that, you introduce that in the joint density, and you decompose the joint density in this way. That's just the product rule. In order to compute that, actually, you just do the conditioning operation we did last time. This thing here is a Gaussian process which looks like that. Remember, we looked at P of F2 given F1? So this just has that same form. It's just P of F given U with these relevant matrices appearing in that form. And what we're doing is we're going to augment our model. So our model says, so this is the way I like to write the model in sort of math form or generalized linear model form. Our model says that Y is equal to this Gaussian process function plus some corrupting noise, which we've assumed to be Gaussian. If you assume it not to be Gaussian, by the way, your life gets a bit more complicated, and you have to use approximations. I'm not talking about that at all today. So we'll just assume that to be Gaussian for the moment. And then this is kind of the equivalent. So for me, this is a sort of what is the Bayesian model that's going on here, which people perhaps don't think about so much. But really, you've got a prior over functions and this very simple likelihood, which is just a product of independent terms. These are just little Gaussians with a mean of F and a variance given by the variance of that noise. So that's the kind of model we're building. Now, what we're going to do is we're going to augment that with these auxiliary variables. So this is still true. right? So all I'm doing here is integrating additionally over U. So I'm using all those complicated rules of probability, the product rule and the sum rule. Isn't probability hard? In order to get rid of this joint distribution and rewrite in this form. Why do I rewrite it in this form? Because if I replaced U with W, this looks like classical parametric Bayesian inference. Yeah? So this looks like a likelihood of P of Y given W, P of W, dW. That would be a classical marginal likelihood in Bayesian inference. But here, what I'm doing is I've introduced U. Now, you might say, well, so you're just turning it back into the parametric model. You could argue. You could say that's what you're doing, so you're just going to have all the negative effects. And people keep saying this. So I really want to emphasize, you are not. Why? Because U is not a parameter itself. It can vary in length. It's observations from the function. Normally, when you're building a model in this way, you have to choose the dimensionality of U at your design time. So before you deploy your model, you're going to say, well, I'm going to make W, the fixed dimensional object, dimension 1,000. That's going to be sufficient. I'll have 1,000 basis functions. In this case, you can change U whenever you like. It's just changing your approximation, it will turn out. You can change the dimensionality of U. That's very unusual. In probabilistic models, you cannot change. You can't just, on a whim, because you've seen some more data, increase the dimensionality of your model without refitting the whole model. Here you can, because U will turn out to be controlling the approximation, not the model itself, because the model's still a non-parametric model. So in that way, everyone gets excited because they see the formula looks similar, and they say, oh, it's a parametric model again. No, it isn't. Okay. So looking at the parametric comparison, this is what we're doing in the parametric world. We're doing something like this, and then I've dropped the x's for cleanliness. So we're getting the P of Y star given Y. And what we're sort of saying now is that this is what we're going to do in the non-parametric world, but U, so we've got the same problem, right? U is now the bottleneck, apparently. Apart from the fact I can change the dimensionality of U whenever I like. I will have to do some work once I've done that, but I can change that whenever I like. So if I see much more data, I can say, let me have 1,000 more U's. Let me throw them in the model now, rather than retraining the whole model. Okay, unfortunately that's fallen off the side, but unfortunately, computing this object here, which is in here and is required for computing the P of U given Y equivalent, is intractable. So we can't actually do this. We don't do this. Because when I say it's intractable, it's not intractable. You can do it. But it's cubic complexity in the data. So you're just giving yourself the problem you had in the first place. Right? So it's totally tractable, but you will require it's basically the posterior over U given Y, so it's the same as the P of Y star given Y, right? That's P of Y star given Y. You can't, just by keeping U small, by keeping Y star small, you don't gain on your computational tractability. So unfortunately, computing that's intractable. So this is where the variational bound comes in. So what you do is you look at this object here. So now this is P of Y given U. This is like our effective likelihood in that model before. I've dropped P of U. I've left it to one side. In the approximations, sometimes you reintroduce P of U and integrate it out. Sometimes you leave it out. Depends what you do next. But this is the key component. This is the variational elbow that David Bly and Shakir so nicely introduced on this likelihood here. So we're just introducing a variational approximation, Q of F, and this gives us a lower bound by where we've got the log here, the Q of S on the outside, the Q of F underneath. This is Jensen's inequality that gives us this. And we're left with this KL divergence, where the expectation is under the approximation, which is the standard variational KL divergence. Now, this is the fun bit, and this is, so I had a postdoc, Michalis Titsias, and when he was a postdoc with me, he pointed this out. We already had these sparse approximations, but Michalis spotted you could do this. If you set Q of F to P of F given U, this is an unusual thing to do in a variational approximation, because it appears like I'm setting Q of F to be a part of the model, right? The P means it's in the model. But why is this not part of the model? I mean, it is part of the model, but what's special about it? Anyone? Where was U in the original model? Wasn't there. So P of F given U is made up, right? It kind of isn't made up. It has to still be a form, it has to be coming from the Gaussian process, but I can control what U looks like. So that's the trick here. That you've introduced auxiliary variable. It's a really nice trick. You've introduced this auxiliary variable. You've then forced it to be some part of the model, but it's part of the model that is controlled by the auxiliary variable. So you have control over Q of F. So that's sort of, Michaelis is one of those thinkers that sees these things. Now, when you do that, what happens is, why that's fun is because that cancels now. And this is just left as P of F given U log P of Y given F. Now, further, because P of Y given F typically is a likelihood, and this is the really nice trick, factorizes over Yi. Where did I put that? Here. Yeah? That means that the result here, the expectation of log P of Y given F, is actually the sum can come out, because this factorizes. So this is a series of one-dimensional integrals. Yeah? Very nice. So once you've got this, now, in order to, what I'm going to do is bound P of Y given U, because that's the thing I'm going to insert back in. So I just put an exponential on it, and it keeps the bound, right? It doesn't affect the bound. I've got a bound on P of Y given U that has this form, where actually there's a sum there, there's a product there, which is a sum in front of this log, which is a sum there, which comes out as a product here. So this thing now factorizes. So this looks like a product over Yi given U. And that happens because of this assumption, which is not in general a correct assumption. But you can see when this assumption becomes correct. So this assumption becomes correct when this KL divergence, which is the KL with that P of F given U, is 0. And this does happen. It can happen. It's very unusual to have these approximations where it can happen. It can happen. It definitely happens if you set U equal to F. Actually, that definitely happens, but you don't gain anything computationally. But what actually you can show is that this bound is 0 if all the information about Y is given in U. So if Y is giving you no additional information over and above U. Now, how can that happen? Why is that a potential thing that is useful that can happen? Well, if Y is very noisy, right, then there's not that much information in each observation because there's so much noise. And you don't put any noise. Well, you can, for odd reasons, put a little bit of noise on U, but you typically don't put any noise on U. So you can like have 1,000 noisy data points and say, well, instead of that, I can store all the information that's in those 1,000 noisy data points with 10 clean points. And when you're doing these inducing approximations, you're minimizing this KL divergence. So it's the classic elbow. So you maximize this maximize the likelihood. That would maximize the KL. So there must be a negative sign. That sign must be wrong. Thinking on the stage there. That sign must be wrong. When you maximize the lower bound, you minimize the KL. So there's probably a sign wrong there. And therefore, you are constantly, as you maximize your likelihood, you're either improving your model or you're compressing more information into U. And that's the trick that's going on in these inducing approximations. It's very cute. I like it. I sort of even think of it, I mean, at my most outrageous, I kind of think it's sort of humans kind of do this. You only remember, you don't need to remember. What in effect is going to go on is you don't need to remember everything you've seen in the world, right? But you do remember the trajectory of events. The trajectory you remember is your model over the Gaussian process, because these two interact, as we'll see in a moment when I show some examples. And then you remember some sort of like episodic events, very specifically, which allow you to reconstruct that trajectory. And humans do something like that, and they incorrectly reconstruct the trajectory when you ask them questions about events that happen very quickly, because your brain is clearly a Gaussian process, obviously. And if something happens that's beyond its reasoning, it just fits through it and makes up stuff to sort of say that must be true. So I don't know. I'm not saying brains do this, but you know, but they do. No, they don't. Okay, so just to sort of give you an example of how this something looks, this is a Gaussian process fit to a couple of clusters of data. And this is the full Gaussian process. Now, with these inducing variable approximations, if I naively sort of fit the inducing variable approximation and keep the inducing variables fixed with the same, I think with the same parameters. The notebook says exactly, in fact, you can reconstruct this in the notebook when it's available and in the slides. Then this is the approximation you get. Now, if I then choose to optimize the parameters of the model, so this is the approximation by just keeping the initial parameters. So the initial parameters look like they were standard deviation of the whole thing is like, must be 1 1/4 or something, and some length scale which is appropriate, which is the sort of, I probably just use the length scale of the true function. So here in this case, there's too few inducing variables to capture the information. So what happens, interestingly, is the model oversimplifies, because it sort of can't compress all the information that was in these things. And the way it oversimplifies is it actually fits a length scale that's too long. So what happens when you're maximizing these variational lower bounds is one of two things happens. You either improve your data fit, that's the first term. Well, actually, David broke it down at one point into the two terms. The first term you can see is the expectation of the likelihood under your posterior. So he wrote it, he said, oh, there's two ways of expressing. Let's just go back here. And there are indeed two ways of expressing, because there's these two terms here. If I combine this term in here, then this KL divergence, sorry, I have got that KL, yeah, the right, screw it. Anyway, so that KL, that P of F, if I put that into there, then this first term is the expectation of the likelihood under this Q of F bound, the log likelihood. And the second term turns out to be the difference between your prior and approximate posterior. So what's going on in this case, because the approximate posterior is too simple, it actually chooses to underfit the data, because it can do better on the KL by making, what happens is the KL term forces the posterior to be simpler than it should be. And so that's one of the ways that variational approximations can go wrong. But if we then optimize over the input locations for those inducing points. So here, I just kept the locations of these inducing points. So I should have made clear these inducing points exist in the same space as this function, in the same space as f. And these are their inputs. Here, I should have clarified that. But now, if I optimize over their input location, so in this one I'm saying you get to remember 6 things, and you get to remember 6 things at these points here. So an estimate of the value of the joint distribution of the function at these 6 points. It's a joint distribution, effectively, what you're storing. But now, what if I say, well, now you can choose where you want to locate your points. And what you do is you optimize the variational lower bound with respect to these input locations. And now you get something a bit better. So it's not quite right. It doesn't have quite the right error bars. They go a bit wider here, and it doesn't have quite the extent of that bump. So the length scale is probably a little bit too long. So it's still a little bit oversimple. But nevertheless, it's starting to capture that ability to choose the point where you observe the function becomes very important. And these approximations were very cool, because before this, people used to subsample the points where you choose the approximations. In Nystrom, you just subsample these data in some way. So this is a more flexible way of doing that, which we like. And these are parameters of the P of F given U, right? These points here. So they're parameters of the variational approximation. They're not real parameters. If I increase to 8 inducing points, then I get something that's pretty much, there you go, very close, right? So I've reduced the number because, and it's that issue here. These are noisy points and these are not noisy points. So I think if you go to 10, and you'll see it in the notebook, you can actually compute the lower bound on the likelihood. If you go to 10, then you basically get 0 difference between the true approximation, the true and the approximation. Now, another interesting thing about this approximation, which I'm not going to go into now, is you can also qualify how good it is at any given time. So most variational approximations, you don't know when you've hit exact accuracy. But there's a term in this bound that you can measure very simply. It's a trace term. And if that term is 0, then you are 100% accurate. So that's pretty cool. Okay. So now this also, what's fun about this is once we've decomposed it in this way, and what we do is we store this Q of U given F is effectively, I'm just trying to emphasize the dependency on y, q of u given y, sorry, once we've got this object here, that's effectively the information about the training data that we choose to store. Now, what I like about this is, although it's true we can change u at any time and increase it to improve our approximation. Yeah, go ahead. Yeah, it's a great question. I think that, to my mind, it's going to be very application dependent. One of the great challenges of GPs, I think for spatial models this works pretty well. But for temporal models it's a bit odd because in time you've got to keep putting new inducing points up ahead. So a lot of it depends on what you're going to be doing. I think these approximations are really elegant and that they have another characteristic, which is you can put a lot of creative design into them, otherwise known as hacking. Now, the problem with that is I think you only really realize the power when you get a large population of people using them and being able to deploy them and create them rapidly. And I think that we're missing the software tools to do that. So if you look at the literature, you'll see a number of papers, which I'm getting a bit bored of, where someone says, hey, I've got a new Gaussian process approximation. You'll see very few studies that are exhaustively studying these approximations and how they work. Why? Because Gaussian processes are a very flexible model. And in some sense, you could argue that your creative work in this approximation is akin to the creative work people are doing with their neural network architectures, in some sense. Now, why are we seeing so much progress in neural networks? Well, because there's 8,000 people running TensorFlow and PyTorch and trying things that they can think of and try very, very quickly. And I think we're not in that position with Gaussian processes. So there's definitely, I have some instincts from things I've tried. But I think we'll only really start learning how to do that when these approximations are easier for people to understand and deploy, because I think that it's absolutely right. You know, if you do this well, you get a great result, and if you do it badly, you get a poor result, and people just don't have the intuitions about yet. So that's one of the reasons we're so focused on software, rather than, hey, I've got a little extension of these algorithms, because I believe in these approximations. I think it's just too much effort every time you have to derive a new approximation at the moment, because you don't have all the autodiff tools and everything else laid out. And once we get that done, I think we'll be able to much more quickly explore which ones are working. So, but this decomposition means that we can, Nico. Yeah. Yeah. Great question. Yeah, I love that thinking. And you see that that relates to the previous point. Yeah, absolutely. But the value of doing that, and I think totally that's something you should do. So like in a spatial model, so let me put how I thought about that question in one way. If I'm modeling a large spatial process and I only care about what's going on in Stellenbosch, I could just put inducing variables around Stellenbosch. I don't need to care about what's going on elsewhere and make predictions here. So that also somehow means that I could do things like I could try and separate, so I could then have a set of inducing variables around Cape Town, I could have another set around Nairobi or something like that, and try and do local computation with those inducing variables when I'm doing test predictions in those regions. I think it makes a lot of sense, but like so many things, and I think this is so important, like so many things, they only really make sense when you've got an application, when you're going to do something. And the worst thing about our field at the moment is everyone jacking around with combining approximations without doing anything. So you can do anything if you're not doing anything, if you see what I mean. I think it's okay. Here's how I reconcile it. I think, so I have this philosophy. So in Sheffield, before you were, a long time ago, when then like South Africa bought Sheffield knives and everyone else did, before you were allowed to make those knives, you had to go through an apprenticeship. At the end of your apprenticeship, what you did is you made a really complicated knife. Why did you make a really complicated, sorry, a very impractical knife? because you were demonstrating all your technical metalsmithing skills. You were sort of putting silver plate on the handle. It was impossible to cut anything with, but you were demonstrating amazing technical skills on your knife. And then they said, okay, you've finished being apprentice now, and you can go out in the real world and make actual knives. The very, very best of those apprentice knives may have also been practical, but that's like 1 in 1,000. Most were just showing, I can apply silver plate to this part of the knife. It makes the knife impossible to cut with, but there you go. To me, that's like most of machine learning now. Most PhD students are graduating, demonstrating, I can do really, really technical things. The practical use of the technical things, you can't cut anything with them. But hopefully then they go on to understand how to deploy those things in the real world. I think the gap we are with the Gaussian processes is we haven't got the real world cutting with these things and exploring. And suggestions like that are really, really important for sort of making the next wave of how you make these things practical. But that's a great idea, but I just think it's only a really valid idea when you're demonstrating it in some application for spatial disease epidemiology or something like that, as you see with neural networks, in fact. Because like it or not, they're doing really serious things on problems that were very challenging in the past, and people are being able to do that by sort of changing the architecture of their models very, very quickly and coming up with often quite hacky ideas, which they can then deploy and test very quickly, and then later the theory follows. So it does lead to these other approximations because of this thing here. You can now do stochastic variational inference, what Matt Hoffman and John Paisley and David Bly invented, which allows you to scale your variational inference for millions or billions of data. So this is a large data set. So we did a paper on this. So this is the house prices. The UK is a little bit more densely populated than parts of Africa. So each of these is, yellow is low price and blue is high price. You can see London's high price. I live in this high price region here. I moved there from this low price region there. That was painful. And what we want to do is perhaps build a spatial model of prices. So this actually relates a bit to Nico's question. How do we do that? Well, we did stochastical. This is actually the Peak District. So this is nice to cycle in. That's Sheffield. It's high price in the one corner where the university is, low price in the steel bit. So what we did is with James Hensman and Niccolo Fusi, we applied stochastic variational inference, and we called it Gaussian processes for big data, because in those days, big data was still cool. And this is what you get. You get a spatial model of house prices across the UK. Now, people are actually, now this data set is now classic. One thing, by the way, if you were the first people to use a data set and the first people to deploy an algorithm on that data set, make sure you don't optimize the hell out of it, because you will get far more citations if everyone else comes later and beats you than if you're the number one. It's totally an error. So this data set is now a classic, and everyone's beating us with their approximations for doing deep Gaussian processes. Top tip. And yeah, to be honest, we optimized. We were just trying to beat the batch approach, the best batch approach. So we didn't really optimize the hell out of it. But yeah, we got something that beat the batch approach, much like where is the batch likelihood? Oh, it says it's there, but I can't. Okay. Anyway, you can read it in the paper. Much like David Bly was saying with the LDA model, he was showing what the batch approach could do, and then how the SVI goes through it. So we just did the same thing. I really like that, and this is a very promising algorithm. People are now training deep GPs with variants of this algorithm, doubly stochastic variational inference, and so on and so forth. That's work by Hugh Salimbaney and Mark Deisenroth. To be honest, I sort of feel secure in a world where this will all work out. You know, we don't have it all worked out now, but I do really believe that we have a number of techniques that will take us forward and allow us to scale Gaussian processes to very, very large values. And the sort of issues that were being mentioned are the things we need to address, but basically the fundamentals are there. So, you know, there was a period when I just didn't think that, and I didn't know where that was going to come from. So I'm pretty happy with these approximations. If you want to know this, I love this paper. A unifying framework for Gaussian process pseudo-point approximations to power expectation propagation. This is by Tang Bui and others. That's probably the most modern and up-to-date review of these approximations, and it brings in another set of approximations known as FITSI that I didn't talk about, but they're closely related. And it turns out that these things are all driven by alpha divergences. So the one that I was showing is a variational approximation, but you can do the KL divergence inverted and do an alpha divergence, and that leads to another approximation people have used, and what they show is that there's a whole range of approximations that you can play with in between. Okay. So halfway through. So this was a very important tutorial for me. It was 1997. This is David Mackay presenting Gaussian processes. So I didn't really know how Gaussian processes work, didn't really understand them at the end of the tutorial, didn't understand them for another 3 years, but hearing David and Chris Williams speak on these things was what got me interested in Gaussian processes. And one of the irritating things David did is after you'd spent all that time understanding the paper, at the end of the paper he says, according to the hype of 1987, neural networks were meant to be intelligent models. So you see these things repeat. This is written in 1997. We're meant to be intelligent models which discover features and patterns in data. Gaussian processes, in contrast, are simply smoothing devices. And that is very true. That is true because everything is based on the covariance function. So the covariance function, when you look at the mean prediction, all you are doing is smoothing. And smoothing based on a cleverly designed covariance function. So it's much better than regular smoothing because you can spend a lot of time designing the smoothing, but that is fundamentally true. They're just smoothing devices. How can Gaussian processes possibly replace neural networks? What is going on? Okay, so it took us a while to catch up with David's thinking, but this tutorial really highlights an issue with Gaussian processes. And it's something that also Arthur was talking about, in effect, when he was talking about the failure of MMD to discriminate images. Well, because those kernels that he's using are also smoothing devices. In fact, kernels and Gaussian processes have a lot in common. And he had to start introducing structure into the kernel. Right? So you might think, oh, well, but it's still a kernel. It was still a kernel. But what he did is he put a load of parameters in the kernel. What he did is he fed into the kernel a convolutional neural network. And by doing that, he's created a number of parameters in the kernel. Now, that does two things. It puts you back. It gets you out of this problem, but it adds a load of parameters. So let me try and sort of explain that. So my deep neural networks sometimes go upwards, which is different to other people's. So this is a fully connected deep neural network. And I've got some inputs here and some hidden units at each layer. And this is a fully connected mapping. I'm not doing any convolution stuff here. So what we can see is, sorry, this is a little bit small. What these are saying is that each of these layers is just a set of basis functions. So if these are like ReLUs or tan H's, then each of these layers is simply a nonlinear function of W times x, where x is the input. This one is a nonlinear function of w times h, where h is this activation at the previous layer, so on and so forth, until at the end, I'm saying y is the inner product of this vector here and this output here, giving me my output function. So it's not quite basis function models stuck on top of basis function models, right? Because there's not a function going on in between. So you're going basis directly into bases. But one of the problems with these models, and which things like dropout were designed to deal with, is that they like very large numbers of hidden units. So if I have 1,000 hidden units in this layer and 1,000 hidden units in this layer, I immediately have 1,000,000 parameters in this matrix here. So dropout is kind of dealing with that because it seems that they need very large numbers. I don't know what the latest thinking is, but when I was first looking at this, it seemed you need very large hidden layers, but you were tending to have problems if you didn't include dropout. So mathematically what's going on is this. You've got an input here. There's a basis function here. In the one layer system that I introduced with the Gaussian processes, it was just W transpose that gives the output. But now that's fed into here, right? So this overfitting problem, well, that's one solution. Now, when I first proposed this, no one had done it, but I think someone has done it now. Another solution is to parameterize W with its so-called SVD. This is like classic. This is just like immediate for people who know PCA and stuff like this. If you've got too many parameters, then rewrite with an SVD, and you can actually drop that diagonal term here and just actually have two. You don't even have to have these orthogonal. You can just have two matrices, U and V, two general matrices. So you're effectively saying that W is low rank. So as long as U is sort of K1, where K1 is the input layer dimensionality by Q, where Q is the rank you choose, and V is K2 by Q, this gives me a K1 by K2 matrix, but it's sort of somehow reduced rank, right? It's not fully parameterized. This has K1, K2 parameters in it. This has K1Q plus K2Q parameters in it. So that's what it is, right? So that's the approximation you're saying. I don't know what that says. That's the approximation you're saying, that U times V transpose is equal to W. So if you were to replace, and actually someone who knows about neural networks will tell me what they're called. They do this in neural networks nowadays, and effectively that's like adding linear hidden units in the middle. What are they called? They've got a name in neural networks. I don't know. So we call it a low rank factorization in maths, and in neural networks they're called neurons. So given x, you have this intermediate variable that I've called z, which is now v1 transpose x, and then that's being multiplied by u to effectively give me what was w. So I've got this rank reduction in the middle in neural network visualization. Okay, now the cool thing is that that is starting to look a little bit more like a basis function model, because, okay, that's an input. Where do I need to look? Let's look at Z2, which is V2 times H1. But H1 was a basis function of U1 times Z1, which was its input. So that object there, the mapping from Z1 to Z2, is just a standard classical basis function, but it's multivariate, right? So it's a vector output on the basis function. So I can rewrite each of these. So if I sort of say Z1 is just like a linear model, and then Z2 is like, these are vectors, right? So it's not single output anymore. They're vector-valued basis function models, but you can do that. There's no problem with that. That's a matrix there instead of a vector to make that happen. Then you're basically building up a series of basis function models, stacking one into another. So basically, that's what you're doing. You're saying that Z1 is some function of x, Z2 is some function of x, Z3 is function of x, Z4 is function of x. Now, if I put a Gaussian process prior over these functions, I'm just doing what I did when I was waving hands in the last lecture and expanding the number of bases in each layer to infinity. Okay? Now, you can actually, so you sort of think, oh, do you have to do this thing here, this bottleneck? Do you have to do it? No, you don't have to, actually. You can expand all these things to infinity at each layer, and you can expand these things to infinity as well. If you do that, you just get a Gaussian process again with a very complicated kernel. And I think it's kind of obvious to me that that happens. I think since I sort of pointed out, people have written it down more formally, but it's sort of obvious to me that that happens. You can show it in various different ways. People have looked at the sort of kernels that arise, like Cho and Saul looks at what they call deep kernels, and those are the kernels you get. You just get a Gaussian process with this where the kernel itself composes. So the kernel is formed by fitting one kernel into another. So I'm sort of less interested in that for my purposes, for the David Mackay problem. Okay, and so what we're going to do is just put Gaussian processes over each of these. How am I doing for time? Okay. So before I go forward, I just want to sort of say something about how I try and introduce deep learning, because it will relate to some plots I have when I show you results. So this is a Callista Flockhart detector developed by Facebook. It detects other people as well. It's called Deep Face. Only that layer at the end there is fully connected. These are all convolutional layers. I think those two are fully connected. But when I'm sort of talking about deep models, and I try and explain to people what's going on, everyone says, you can't understand what's going on in a deep neural network. Whoa. Well, you can. I mean, you kind of course you can't understand anything, but here's an analogy. So this is a pinball machine from the 18th century, and what I like to tell people is going on is you've got an input, and the input location x is one-dimensional, and it's your location from the left to right in the top of this machine. And your output is where your ball falls out in the bottom on the location left to right. And these nails here are your basis functions. Yeah? And each intermediate group between the nails is the intermediate layer that I showed you in that function there. And that's what's going on, apart from we don't normally do it in 1D, but I'm going to do it in 1D for you in a bit. Normally we do, so it's like playing pinball, but in hyperspace. Because really what happens is Callista's face is a point in like many millions of dimensions. Yeah? So that immediately gives you the sense of why neural networks are so shocking in terms of things like adversarial examples, right? Because all that's going on in the adversarial examples is you're dropping this ball into this massive hyperspace with all these basis functions everywhere, and you're expecting, you're saying what you're saying, oh, if I change the initial condition slightly, oh my God, the classification changes. Well, duh. I mean, it's a massive hyperspace. Of course you can do that, right? So the thing about this sort of analogy is what it shows you is that you will, even with one ball, you have to throw it through the machine, a lot of times to explore where all these basis functions are. And if your ball never goes near the basis function, your basis function will be in the wrong place. And in fact, when you think about AlphaGo, what Lee Sedol did when he won the move is he managed to put the ball in a place where AlphaGo had never seen before. And that's why it played a stupid move at that moment. Of course, once he'd done that, they trained out of that region. In fact, they had it, what was the European champion, Fan Hui? I think they were playing the game against Fan Hui for months before that match to try and get Fan Hui to do that, to play the ball into regions at the top where it was going to go in down regions where they'd never seen before. Once they've done that, they can simulate out. They can start playing games out of that region. But if you didn't find that data point in that region, you've got regions where the model is going to do stupid things. So this is how it looks before training. Look at this. Right, so that's Callista. It was Callista. It wasn't Callista, but classified her as being Callista. And then the process of training is, of course, moving those points around. Okay, just by gradient descent. But these points are, of course, sort of ReLUs. They are a little bit like this. Okay. Now, for the Gaussian process perspective, this has other interpretations as well. Like you can immediately see, first of all, it's a composite multivariate function. So you sort of think once you're doing that, well, a mathematician goes, well, what's the point in doing that? Well, of course, the point in doing this is that these are simple functions, and by combining simple functions together, you get a complex function. And the point of doing it with stochastic processes is that's a Gaussian process. That's the early universe, right? That's after the cosmic microwave background. That's the Earth. If you do that enough, that's what you get. I don't have enough compute to do it, but so that's composition, stochastic process composition. And it has some really interesting effects when you do it with processes instead of just functions. Because when you're doing it with processes, as several people talking about GANs and everything else were describing, the nature of the distribution, the nature of the process changes. This is still a valid stochastic process. It's a new way of creating new stochastic processes that are non-Gaussian. Of course, so they're slightly intractable. Now, I'm not going to talk about how you make them tractable. You can read that in the paper I wrote about with Michalis or in Andreas Damiano's thesis. But the other thing about these objects is they are also Markov chains. And that's led to some nice analysis done by sort of applied mathematicians on deep Gaussian processes to start talking about what the nature of this process is. Because you can use Markov chain theory to start studying what you're actually saying about your data. So I like to draw them that way around. Yep, said all that. The other thing that people always forget, like to me this is obvious and natural. Why did I care about this in the first place? Graphical models. I just happen to be working on the chain. That's all. Because it's fun to start playing with the chain. But in my mind, this is what's going to start happening. Nodes coming off this everywhere. Pulling data sets together by saying, so the example, well, I'll have that example at the end, a health example where you think at the top level, that should be the latent structure of disease as in the clinician's mind, as relating to survival. But at the bottom level here, you get more and more detailed things. That might be the mammogram that shows the cancer or something else like that. Trying to introduce models that allow you to go across all those sort of things. Of course, the challenge is, as people have said, that as you go through these nonlinear functions, you really change the nature of the distribution you're playing with. So a univariate Gaussian through a nonlinear function, basis function model can become very complex even in one dimension. So this isn't tractable. And all the work you heard on GANs from Sebastian and everything, and Arthur and everything, is all about trying to deal with that lack of tractability. Now, it turns out, I'm just going to wave my hands a bit here, with the variational approximation I showed you at the beginning, you can deal with that. You can do another variational approximation, and you can integrate out x. So we have an approach that allows us to put, in this graphical model here, a Gaussian prior. So each of these is a Gaussian process. So what we do is that's a Gaussian process, but we have an approach that allows us to push the Gaussian through this Gaussian process here and reapproximate with Gaussian. And once we've done that, we can chain these things together. So you can now put them in any form of graph. And that's one of the things we're working towards with our MX Fusion software, is enabling people to write down those graphs from the start and have our approximations run. Okay. Probably enough. Okay, so if you do that with linear models, nothing much interesting comes out. So what I'm doing here is just showing you the result of an affine transformation on multiple layers. But when you do it with Gaussian models, fun things happen. Unfortunately, that's a little bit dropping down, but you can see the basic idea. What happens is this square is, I've mapped this through a Gaussian process from 2D to 2D, and it's folded over on itself here, just in that mapping, which can happen. Once it has folded over on itself, that can never unfold. That's what leads to the non-Gaussianity, actually. Remember I said if you make those things infinite, then it's still a Gaussian process. In an infinite dimensional space, nothing folds over on itself. And that's why it stays a Gaussian process. As you reduce the dimensionality of those latent spaces, you get increasing non-Gaussianity. Funnily, I showed this plot at Cambridge a number of years ago, and it triggered David Duverneau to write a paper about this effect, where he called it pathologies in deep models. But, I mean, it's a great paper. A slightly irritating thing about the paper is, if he'd asked me, I'd have told him, well, that kind of only happens in low dimensions for certain covariance functions, and that's what they did in the paper. And it's a property you sometimes want. It's a property you sometimes don't want. So these low-dimension latent spaces lead to this non-Gaussianity, this very complex structure. I'm not going to be able to get the video going, am I? There's a video on the slides online you can look at later, which David used to visualize that. In fact, what you can show, what David showed, after, I think inspired by that plot there, they looked at the derivative distribution of the resulting process, and they found it became more heavy-tailed as the number of layers increased, under particular assumptions. You can make it so it doesn't come more heavy-tailed, under particular assumptions. And then that leads to some of these interesting behaviors, and I'm going to show you them in the examples in a moment. Another very interesting paper by Mark Girolami, Andrew Stewart, and is it Mark Dunlop, who are sort of applied mathematicians, does a theoretical analysis looking at the conditional Gaussian Markov property of these processes and linear operators. They also, I love the paper. If I were to be slight, everyone wants to show that their result is very general, so they don't point out how it's not general. In their case, the way they get that is they assume that each of those Markov those conditional distributions is identically distributed. And that's what allows them to do analysis. In fact, David's showing the same thing. In practice, I've never fitted a model where that's true. So in practice, you can allow each of those distributions to have its own covariance function, and that's kind of important in getting more complex behavior than either of these suggest. So these suggest certain behaviors, they're actual special cases of the model. Okay, so that isn't going to work. So of course, GPI I mentioned yesterday, it doesn't do deep GPs, but you can find in the notebooks how to do deep GPs, and MX Fusion, which we're releasing, is targeted at doing deep GPs faster. Okay, so back to the Olympic marathon data that you saw from last time. Alan Turing, very fast. Look at him. So actually, in the first film about his life, he was a bit chubbier than that, because the actor wasn't quite as fit as Alan. But this is the deep Gaussian process fit. So remember from before, we had this problem with this outlier here and the noise going larger. Now, so this is how the deep Gaussian process fits it. First of all, notice it's not done anything very complicated. It's got the capability, it's 2-layer in this case. I've tried more layers and it still doesn't do anything very complicated because it doesn't need to. It's actually quite difficult to initialize. You can So you can see in the notebook code how I'm initializing this, and you can get, there's definitely multiple local optima, so you can get other fits to this. Of course, you can always check the lower bound and try and select your optima, but you're not going to get away. You're not suddenly killing all the problems you get normally with neural networks by using Gaussian processes together. They all pop up again, initialization problems. But it's quite nice. It has a sort of an understanding that things were large at the beginning and maybe things did flatten, and then these bounds are these error bars are a little bit tighter. These are 2 sigma error bars. Of course, they're 2 sigma, but the underlying distribution is not necessarily Gaussian anymore. So here's some samples from through the system. It does look like it might be broadly Gaussian, but I haven't measured what they are. But these are samples just taken by dropping something in at the top and pushing it through at each layer to find out how it comes out. And you can see you're getting wide variations. So apparently it believes in other people that are just as disorganized as the Americans when organizing Olympics, and some superhuman people. How is that doing that? Well, this is the visualization of what I'm going to show you is the visualization of the input to layer 1. So this is the ear, and this is the hidden layer, Z. And what it's doing, this is interesting, right? So this thing isn't doing that much. Number one, this turns out to be quite important, right? This is the most recent stuff. So you can invert this, because of course it just inverts it the other way. But so actually this looks like it's getting slower, but the sign on the next part shows that this, in the standard model, that would be a straight line, right? So a straight line 1-to-1 going into the latent variable, then you've got the standard model. So all it's added is a slight curve at the end and a little bit of noise. So what's the effect of even that simple curve? Well, that slight curve at the end turns out to be, if we look where it's mapping to about 3. And if you look where 3 is, it's mapping to here. So all the data from the recent years are mapping to that same region. So what it's sort of saying is somehow whatever this underlying curve could be interpreted as reflecting the slowing up of the 1940s. This could be reflected as the other one could be thought of as the fact that, okay, this tapering off here is the fact that we're not getting that much faster anymore. And as a result, you see this narrowing of the error bars in this region. So that's something you're not normally seeing with deep neural networks, because the noise isn't being pushed through, right? So actually one of the most powerful things that's going on here is the noise is coming through. Okay, now I said about the pinball. Of course, this is 1-to-1-to-1, so this is the pinball game. So this is where the ball's coming in the top, and then this is the intermediate layer of pins. And what I'm showing here in the shadows is I can view the ball's transit through as a random walk, right? Such that the random walk at the end, when it reaches here, is equal to the variance of the Gaussian process in that intermediate layer. That variance gets pushed through. So there's an amount of variance on these layers here. I'm not then pushing that variance through the next layer, right? So I'm showing the 2 separate conditional distributions. I'm not showing the joint distribution at the end. So this is less noise on the second one. And what you can see is that people from as far as 1970 are all being mapped to the same place, and then they're just being mapped straight down. And then there's some warping in this section here. So this is just a visualization of those functions. Okay, so the delegata gene data I showed you earlier, what does it do here? I was curious. I'd never run it before. I ran it last night because I'd used it as an example. And the answer is, so that's the GP, the 3 different fits, and that's the deep GP. Kind of nothing. Doesn't really do anything. It just says, sure, what am I going to say? You could probably run all sorts of things and find all sorts of local minima. That's just the minima I found with the standard initialization I'm using. There's the samples. It looks broadly like it's a standard Gaussian process. There's the first latent variable, which is high noise, and there's the second layer. So nothing too much to say about that. When you look at the pinball plot, by the way, if you don't find these plots useful, don't tell me, because it took me ages. If they're totally non-intuitive and have destroyed the entire understanding, I don't want to know. I'm going to keep using them. Step function. So step functions are notorious. You can't fit Gaussian processes to step functions. But remember I said that you can show that the derivative degree increases. The degree of the derivative distribution increases. So meaning that as you go down, for certain parameterizations, as you go down the deep GP, you get heavier tails on your derivative distribution. Meaning that you can get more discontinuous processes. So this is the Gaussian process fit to that, which hates the discontinuity. If you are dealing with discontinuities when fitting Gaussian processes, the right thing to do is to parameterize them. You can parameterize them in the mean function, or you can, I mean, there's a number of ways you can parameterize them. You can deal with discontinuities, but you have to know where they are, and you have to put a parameter in for them. And that means you're going back to like a parametric formalism, right? You're putting parameters back into your non-parametric model. You don't get the ability to decide there's a discontinuity sometime in the future you didn't know about, yeah? You have to know where they all are. That's like a parametric model. So we don't really like that. So this is the step function with a deep GP of like 4 layers. Now you might already be looking at it thinking, oh, but it's still smoothly interpolating. It's not. What's going on is you're looking at the mean and the variance as propagated through. But if I sample, look where the samples end up. So where it knows where there's data, occasionally it thinks maybe things jump up or jump down, but basically it's confident that things are either 1 or 0. So this mean here, there's no mass really in this intervening section. Occasionally it thinks maybe things jumped, but that is, I think it's called Schottky noise. So normally you would only generate that with a Markov jump process. I mean, of course, you could argue it's overfitted in some sense because the function could be up here. How does it do that? Well, it's kind of obvious when you look at it. If we look at each latent layer, right, and this is 4 layers combined together, each one just keeps putting sigmoids in, yeah? Make sense? So what you're seeing now is this really powerful, massively extraordinary powerful Gaussian process says, well, the way to fit that step function is just to do a convolved series of sigmoids. Very expensive way of combining some sigmoids together, which does, of course, give me a step function. Each sigmoid itself is not got a step in it, but when you combine them together, as you can see in the very interpretable and useful pinball plot, that's one. I think this one looks like a Space Invader. I was particularly proud of this one. You can hear the whap, whap, whap noise. So look, you can see it does something a little bit funny at the beginning. It's sort of, there's a couple of, that's these curves. That's characteristic of these type of curve behaviors going on. But basically, it ends up mapping them all down to one point. So if you're in the middle here, of course, there's a lot of uncertainty as well. Be careful. It doesn't mean if you start here, you necessarily end here, because there's uncertainty that could push me all the way over here, and there's uncertainty here that could push me all the way over here. And that's why you're getting the transitions as well. So you've got a strong probability of starting here and ending up here, and starting here and ending up here. But basically, the main flow, as shown by the sort of these straight lines which connect the means, is to one side or the other. Motorcycle helmet data. This is one that's quite widely used in people caring about noise which is non-stationary. What's going on here is a motorcycle helmet is being sent forward at some constant speed, and then it's experiencing a collision in a test. I think not on a motorcyclist itself, but as a test. So this bit here is like when the motorcyclist is the force it's experiencing. This is the motorcyclist moving forward with no force, and then this is the collision. And then those are the sensor readings from the collision. So that's the Gaussian process fit. Of course, it again has large variance here because it's constant variance. I mean, there's ways of dealing with the constant variance issue, other ways. But we're doing, it just happens to be one way of doing it here. So this is the deep GP fit. Now, be a bit careful because you might think again, oh, these error bars here are wrong because they go too high there and too low there. Yes, but this is a very non-Gaussian distribution in this case. So if you look at the samples, none of the samples go up in that region there. And the samples do fall in this region here. And how is it managing to do that? Well, again, it's got some input which has some noise and some particular shape. This characteristic here is, again, how it's choosing to do that stationary bit with low variance. It's mapping the first series of points all to roughly the same region. And then a very tight chirp. So that's probably something like what the force that the motorcyclist really experiences. And maybe you could argue something that's coming in here is perhaps the noise on the sensors, or the force that one would theoretically experience. And then the combination of those two together is the first mappings are all being put into this region here, which is low variance. And then this whole chirp is being moved around because it's in that region there. So there's some uncertainty on the input location of that chirp, and that uncertainty is causing this curve to effectively be moving left to right, which allows noise to come in down here and no noise up there. Alex? I don't know, actually. It's a good question. I think it's so diffuse, it's sort of meaningless. I mean, yeah, maybe there's something odd going on. I looked at it. I was initially worried. That's the problem. You get worried when you sort of see it in these forms. Oh, come on. Yeah. In this form here, because you think, oh, that's the mean function. But when you look at the actual what's going on in the process, it's, well, like this error bar is well below. This distribution is very different from the Gaussian distribution. So I'm not sure whether, yeah, I don't know exactly. It's a good question. And then the extremely interpretable and very useful pinball plot. What it's saying here is at the beginning, look, everything's being mapped towards 0, yeah? So you can see how it's doing that. And then why it's a bit more complicated is because this is the chirp, right? So everything's being swung around and then being mapped again. The end state is also mapping towards 0, but presumably there's some noise still at the end state, so it's being mapped around 0 a little bit. Okay, there's one last example, but I'll fly through that. It's a sort of robot high-dimensional example for the regression. Now, these models can also be used for unsupervised learning. I can just drop the inputs. I don't have to have the inputs because white noise is a Gaussian process. It's just one without inputs. So I don't know. I guess it's so natural to me that we often don't emphasize that. But you know, the whole formalism is designed for supervised and unsupervised learning. But in this case, what I'm going to sort of show is an example where we're doing some sort of joint graphical model of the type I started describing. This is hand-coded. This is work that originally I think I did back in 2008 and was recreated by Andreas Damianu, which was, you're interested in a situation where you've got two people walking and high-fiving each other. So here we have a shared space because part of their action is shared, they're high-fiving, and part of their action is independent. So this is a bit like the half-sibling regression that Bernard mentioned. And we have really great models for doing that type of thing. Not directly, unsupervised learning models. Bernard was doing it in a direct way to find those exoplanets. And you can easily build models of this type. They work very well. There's a particular model of this type which was created, we called it manifold relevance determination. And it's basically exactly the model Bernard showed, but you learn the dimensionality of these private spaces and shared spaces. So you sort of unpick in the data what's shared and what's private, and it does that automatically, and it's an unsupervised model, whereas what Bernard was doing was sort of regressing from one to the other in the half-sibling regression. This is a digits model where we've got a deep unsupervised neural net, Gaussian process operating on digits, handwritten digits, and it's a number of layers. Each one is two-dimensional, so you're just seeing the location of the digits in each layer. Importantly, I know that you can do this with GANs and variation autoencoders and everything else like this, but I don't know if this is still true, but it certainly used to be true that we can do this with much less data than any of those. So this is very low data. You'll see in the example in the notebook where you can recreate this. These are the samples of the digits. These are regions between digits, so they're sort of, but they're regions where you're on top of the digits. It's like moving around the latent space in the same way Sebastian showed you for the GAN. And this is all done by maximum likelihood. I mean, why do we struggle? In the end, we don't really focus on images because for similar reasons to some of the stuff that Arthur was saying. When you saw how they generate images with GANs, they've got these inverse conv layers and everything else in order to get it to work. That maybe you could do a lot of work to make that a Gaussian process, but it doesn't seem to be the strong point for these models. We're sort of more interested in general modeling. The world isn't just about images and text. So this is kind of where, for a long time, I've had this diagram for years, I want to take this stuff, is that if you're looking at health or something like this, there's a number of different things that come into it, some of which are present sometimes and not present others. And you can handle all of that within this framework. You can handle missing data. So if you've got the gene expression for one patient but not another, that's no problem because it's a probabilistic graphical model and you could just take it out. survival analysis. So we did some work. Alan Saul was a PhD student of mine, where we worked quite hard, and we didn't get there because I don't think we were using a sophisticated enough model to combine survival analysis data with sort of richer representations like gene expression or measurements from the blood, higher dimensional measurements. It's very hard because survival analysis data is very weak in the likelihood sense. So it turns out, like, if you look at survival analysis, you're seeing a population, how many people have survived to a certain point, when people died and disappeared, all this censored data. The amount of bits that gets you to accurately predict that in the likelihood sense is very few. So models much prefer, if you're doing a sort of unsupervised learning models, to care about accurately modeling gene expression, which you don't care about. And that's a major problem, I think, for probabilistic modeling in general, is that you often care about one value like survival analysis, the survival time, but you're also trying to jointly model some other value because you're trying to deal with missing data. And then what you tend to find is you really model the gene expression. Well, I mean, you end up modeling the gene expression well and ignoring the survival analysis in an effort to improve the gene expression. My theory is if your model is complex enough, that stops happening. But we haven't proven that yet. Of course, in the meantime, what we do instead is we regress from gene expression to survival. Yeah? And then you're not modeling the gene expression data. You're just regressing from it to survival. But that gives you problems if the gene expression is partially missing, or something like that. So that's kind of why you would really like to be able to do joint models. Oh, so there's some papers there of different people doing it. Deep survival analysis, that's from David Bly's lab. Oh, we also did recurrent Gaussian processes using all the same tricks, right? So, and Alan Saul, as I said, survival analysis, that was his PhD thesis. Gaussian process-based approaches for survival analysis. Okay, where am I? I've got 9 minutes left. I'll give you a sort of overview. So there's an amount of stuff that's left in the slides is talking about how you can deploy these methods in particular areas. In particular, this is the big thing that I care about, the field of uncertainty quantification. So uncertainty quantification is the science of quantitative characterization and reduction of uncertainties in both computation and real-world applications. It tries to determine how likely certain outcomes are if certain aspects of the system are not exactly known. This, to me, is super important. When so in my day job, which is in the Amazon supply chain, there's an enormous amount of physical things going on, many of which you're uncertain about at any given time. And there's a very large number of decisions being made on a daily basis of what to buy and where to put it in the supply chain and how to deliver things. When you start looking at these real-world problems, you get these really interesting trade-offs. So, for example, when you click on Amazon's website, it will promise to deliver you an item within 9 hours' time or something like that, right? That has to be computed, that promise has to be computed like that, because otherwise it delays the loading of the web page. And it's known if you delay the loading of web pages, then you get less interaction. Of course, you can later decide how you're going to actually deliver the item. You don't have to deliver it in the way that that algorithm decided to. When you get into real-world applications, this type of stuff happens all the time. You're going to make a decision multiple times. People are like, why don't you just make the decision once correctly? Well, because one time you're doing it under a time constraint, and later, once the order's made, you're doing it at its leisure. So you actually end up having a constraint of how long you're going to take to fulfill your item, which is dictated by what the website says, right? And you end up having to I mean, humans are doing this all the time. You're sort of looking forward, making plans, making predictions without full data, and then finding yourself in a difficult situation. When you start looking at a complex system, and I would argue, I mean, you can argue back, but no one's argued back and persuaded me, Amazon's supply chain is probably almost definitely the world's largest AI. Just in terms of the number of decisions it's making every day and the amount of money it's spending, because not all the buying, but a large portion of the buying is automated. Right? So when you're dealing with a complex system like that, not just playing around with, oh, I've recognized this, these sort of issues come up. And one of the ways that they come up is you want to quantify uncertainty. So what UQ and emulation is about meta-modeling your system. So there's a very complex system that's in the world. To give you another example of it, we used to work before when I was at university for a leading Formula One team. And leading Formula One teams, they do a large amount of effort to design parts that they put on a car. So they do computational fluid dynamics, and then once they've done that, they decide what to test, and they decide what to put in the wind tunnel, and then they put it on the car and they take it to the track. And all this is giving them different informations. If you don't know the uncertainty associated with each of those pieces of information, you can't make decisions about what to do. And the art of uncertainty quantification is basically the following. You take each of those components and you model it with a Gaussian process, or your favorite model that has uncertainty. You can use a Bayesian neural network, if you like. And then you use that to calibrate how much information you're getting in from each part. So in any complex physical system, that's what UQ is about. One example of that, a very simple example, is Bayesian optimization, where you incorporate the decision as well. You emulate the system you're going to optimize. You have an acquisition function which encodes the decision, what you care about in terms of your optima, and you turn a handle. Instead of optimizing the system itself, which is typically some physical process or something that's slow to operate, you optimize on the Gaussian process, the surrogate model, the emulation. And that's basic approach. That's the thing I'm sort of most interested in, is using these models for emulation, for surrogate modeling. It means you can do things like, once you've got them, you can do sensitivity analysis. And as is very often the case in a complex system, you have one simulation or physical model feeding into another. And if you model each component with a Gaussian process, of course, what you get is a deep Gaussian process. And so you can model the whole pipeline. And for me, this is like a massive area when you're deploying machine learning in the real world. So that things like combining the CFD, wind tunnel, and track testing. Another thing in Formula One they do is simulation for race strategy, but that's slow, and what you can do is you can fit a Gaussian process to the simulation and predict what the strategy should be. There's some examples here of the mountain car, which is an old reinforcement learning example, just using emulation to train how to do the mountain car thing. So this is Bayesian optimization of the mountain car, which is an example of surrogate learning. I know this isn't an impressive reinforcement learning example, but still, we like it. And then one of the things we looked at is when you can emulate the dynamics of the car. So, of course, the mountain car, it takes no time to run the dynamics. But in a real simulation, it might take a lot of time to run the dynamics. So just as a demonstrator, what we're using, because we're using OpenAI Gym there, we're showing you can emulate those dynamics. So this is a Gaussian process emulation of the dynamics. And instead of optimizing using Bayesian optimization on the system directly, you can do Bayesian optimization on the emulator and still get the same result. Now, the Gaussian process is slower to run than the simulation of this car's dynamics. So this is actually slower to do. But there's many, many complex situations. Climate modeling is another big area where this comes up. Multi-fidelity, multi-fidelity optimization we do with deep Gaussian processes. So the idea here is that this emulates a low-fidelity simulation. So that's very common. You've got one simulation that is poor fidelity. It's not got enough granularity, but it's fast to run. Or it works well in one region. And one simulation that is higher fidelity. And here, you're trying to jointly fit them. So we have another little example of that. Of course, it's just the same result with the car. But we basically, in this case, we built a corrupted simulation, one that wasn't an accurate simulation, and combined the two, and you jointly model the uncertainty between the two simulations, as well as sort of fitting of the mountain car. So this is all going into a framework. This is a separate framework from the underlying Gaussian process framework called EmuKit, which is now online, and it's BSD MIT licensed on GitHub. We would love people to join with us and sort of contribute to this effort, because we just think it's going to need a whole community to do this. As an example, sensitivity notebook, all those things, blue things are links to go and look at. And then eventually, it's going to do all these different things. Multi-fidelity emulations, what I just showed you, Bayesian optimization, experimental design and active learning, sensitivity analysis of the system you're looking at. That turns out to be very often very important. Bayesian quadrature, that helps with the sensitivity analysis and other things. And then that will all be driven by our modular probabilistic programming framework. Doesn't have to be, actually. We've built it in such a way that you can use whatever uncertainty models you like. But this is the uncertainty models we're now mainly focused on, as well as GPy. In the end, this new framework will become the computation engine for GPy. It's based on MXNet and gets the automatic differentiation from there. And the key thing about it is the linear algebra operations you need to do to be numerically stable and efficient in Gaussian processes. We put a lot of time into thinking about those. So if we had to pull it off MXNet and put it on PyTorch, then we could do that as well. Okay, so that is, there's a little bit about MX Fusion at the end, but I'll skip that and just say thank you.